For this scenario, we're looking at some sort of rocket turning on its engine, which is providing some sort of acceleration. Now, notice that I'm having the velocity here to the right as some positive value, while the acceleration is negative, which means that I'd expect the acceleration to be pointing leftward. So if I were to draw a picture of the rocket, I could imagine it having a shape like so. Its engine's blowing like this, but I would be describing its velocity vector, at least its initial velocity vector in this direction, and the acceleration in the opposite direction. So, because those two vectors are opposite, I would actually expect the rocket to eventually slow down, stop, and start reversing direction. So while it's initially moving to the right, it should slow down, stop, and then move back and accelerate into the leftward direction. So, we want to try to figure out how much time it's going to take here for it to go some certain displacement. And also, like I said before, the rocket's going to go so far forward and then come back. How far forward will it go before it begins reversing? So let's try describing that. From our kinematic equations, we could start with the one that describes displacement generally, x equals next plot, x naught plus v naught t plus 1/2 a t squared. So given the information we have that we are told the displacement, we know x minus x naught, so we know the difference between those two values. We are given the initial velocity, we are given the acceleration, and we're solving for time. So this is a very useful equation to use. So it's now just basically a matter of solving for t. And you're going to notice here, though, since we have t and t squared, and that's what we're solving for, what we're really doing then is solving a quadratic equation. So remember that the quadratic equation has the following form, that it is the form where you have a times variable, I'll use t in this case, t squared, plus another constant b times t, plus some whatever constant c equals 0. In this setup, the solution that you get for the quadratic equation is negative b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. Alright, in this scenario then we want to try to match up this general form of the quadratic equation to what we have here. So in that case then, we're going to set up the equivalences that a is the constant that goes with t squared, so in that case a, this capital A here, is equal to 1/2 a, the acceleration. B will just be v naught. And as for c, that's the term that doesn't have any multiplication of time together. So I technically need to bring this x term to the right side of the equation, so I have to subtract both sides by x. So that would give me x naught minus x on the right side, and I'm just going to reverse that around to give negative x minus x naught. The reason I decided to put it into that form is simply because I know the displacement is supposed to be 146 meters, it's supposed to be some positive quantity, so this way it's easy for me to just plug in 146 kilometers and then the minus sign there. So I know all these values then, I can plug it into the quadratic equation, and that will give me 2 different possible values for t. Now, because it's a quadratic equation, it's possible that when I take the square root, I take the square root of something negative, which means it would give me imaginary times. That would not be good. I shouldn't have imaginary time as a possible solution. That might be a sign I made some sort of mistake. I could get a positive or negative time, and in that case then I would exclude the negative time because we are saying the rocket started at time equals 0. Before then, there isn't any rocket going, and we're not describing with this equation what happens before the rocket motor turns on. If I go through and I find the solution when I get 2 positive values, then there's some interpretive flexibility with this problem. And in fact, that's what you're going to find, that there will be two positive solutions to this equation. When I go ahead and punch in for time plugging into the quadratic equation, I find that the two possible times that I get are 6.6 seconds and about 110 seconds. Why we get two solutions? It's a little bit clearer if we graph the equation like so. So if I have the equation basically as a function of displacement and the variable of time, I'm going to get something parabolic, and since the acceleration is negative, I'm going to actually expect a downward curving parabola overall. So if to the right here is the time vector, up here is displacement, or x minus x naught, the graph is going to have a shape something like so. And this is basically kind of what we'd expect. We start at position 0, and eventually, because the rocket is slowing down, it'll reach some sort of maximum displacement, and then it'll start reversing and coming back to where it started, and continue going down and going backwards from where it was. So this maximum, if you graph it, you're going to find, in fact, you're going to find later for the next part of this problem, that it's significantly further than 146 kilometers. Not to scale, but 146 kilometers is right around here. So if we were to draw a line then from there, we basically see there are 2 points where the rocket ship will be 146 kilometers away from where it initially started. So in that case, there are, like I say, 2 possible times we would expect that the rocket would have that displacement from the starting position. If you saw a problem like this, you could easily say that either answer is perfectly fine, but you probably would choose the first one simply because that's going to be the first time you have that sort of displacement. So, most reasonable probably then to say for a problem like this, that you're looking at this point here when you're 146 kilometers away, and that's at about 6.6 seconds. And otherwise, 110 seconds, that's almost 2 minutes. So definitely much further away. As for figuring out how far away the ship will be from its starting point when it finally stops and reverses, well, we could, instead of using the original kinematic equation we were doing, we could look at another one. Like I say, ultimately we're looking for when the ship reverses direction, and that will happen when the ship's velocity is 0. And we know a kinematic equation that describes the velocity of something under constant acceleration at any given time. It's a function of its initial velocity plus its acceleration times time. So we could use this and figure out, well, how much time goes by until the ship stops. Again, we know v0, we know acceleration, so we can solve for t. We could use another kinematic equation as well if we use v squared equals v0 squared plus 2a x minus x naught, the displacement. And this one we don't even have to solve for time necessarily. Again, we know we're looking for when this velocity is 0, when it's stopped and starts reversing direction. This we are given, acceleration we're given, and so there's only one unknown to solve for. So we could use this equation, solve for time, and plug that into another kinematic equation, or we could use this one, and probably using one equation is preferable than rather using 2. Less chances of mistake, saves more time. If you calculate time in one case, plug into another equation, the error from just the calculating and plugging it back in builds up. So best to use as few steps as possible. So we're saying the final velocity is just 0, so we can do that. And we're trying to solve for the displacement. So just quickly doing the algebra, we're going to see then that v naught squared divided by 2a is equal to the displacement x minus x naught. Go ahead, plug in our values. We notice, of course, there's a negative sign here, but we have a negative acceleration, so the displacement should be positive, as we would hope. When I do so, I'm going to get 684 and some, and of course, if I want to be careful about sig figs, I can only justify 2 significant digits, so I'll say about 680 kilometers. Okay, and just also one minor point that everything I was given was either in units of kilometers per second squared, or time is in seconds. I could have converted everything to meters and have everything in SI units, and then make sure I work everything back, but since everything was already in some set units, I didn't necessarily have to change anything. So when I plugged in values for velocity and acceleration here, this was in kilometers per second, this was in kilometers per second squared, and the units still work out, but the displacement comes out to be kilometers. I didn't necessarily have to convert this to meters per second and this meters per second squared, get this value in meters, and then convert it back to kilometers. Wouldn't have necessarily been useful here. Other cases it might be, but in this one, I could get away with just leaving everything as it was. And of course, just a little bit of a sanity check. We notice, of course, that distance is further away than 146 kilometers, which we were initially looking at for the first part of this problem. So in that case, the rocket goes past 146 kilometers, reaches this maximum, and that's when it begins reversing and starts backtracking. It'll be at 146 kilometers again, and then goes backwards, and we'll keep going with a negative velocity indefinitely until we turn off the engine on this rocket.